Good morning. Welcome to our webinar. My name is Andrew Mills, and I'm a Staff Research Associate in the Electricity Markets and Policy Group at the Lawrence Berkeley National Lab. And I'm also one of the co-authors of this report on the financial impacts of net metered PV on utilities and ratepayers. Welcome again to our webinar, presenting a summary of this report. Here to present are the other two primary authors of the report. First, we have Galen Barbos, a research scientist, and Andy Satchwell, a Senior Scientific Engineering Associate, both also in the Electricity Markets and Policy Group here at Lawrence Berkeley National Lab. A few notes on the mechanics of this webinar. We will have time for questions and answers at the end of this session, probably about the last 10 minutes or so. So if you do have any questions that arise during the webinar, go ahead and enter your questions on the chat window at the bottom left of your screen, and you can do that at any time, and we'll try to get to as many of those as we can during the question and answer session. And with that, we'll go ahead and get started by first handing it off to Galen Barbos to begin.
All right, thanks, Andrew. Welcome, everybody. So the material that we'll be covering here is based on a report that we issued last month by the same title. And given the amount of time that we've got available for the webinar, we'll really only be going through some highlights from the report, and we'll certainly need to gloss over some of the underlying methodological detail. So for those that are seeking a deeper understanding of the results, I would certainly encourage you to take a look at the report itself, and we'll provide a URL at the end for the report if you want to find it on the web. The other thing that I'd like to mention before launching in is the lineage of this work, which is very much an outgrowth of the research program that a number of folks within our group, Andy Satchwell here, as well as Pete Kappers and Chuck Goldman, have built up over the past 5 years or so, and that revolves around looking at the utility business models issues related to energy efficiency. And so this is certainly an outgrowth of that work in a number of ways. So I'm going to start off with a bit of an overview of the present study, and we'll then hand the baton off to Andy, who will take us through the results and the remainder of the presentation. In the interest of providing some sense for where we'll be going, I thought it would be useful to start off just by characterizing in general terms what kinds of conclusions this analysis may or may not support. Although it may be perhaps somewhat unsatisfying, we do like to stress that the results from this study really do not support broad, overarching statements about how distributed or net metered PV impacts utilities or utility ratepayers. Rather, at the end of the day, what the analysis really shows is that these impacts depend critically on the particular circumstances of the utility, and they may or may not be significant. If the impacts are significant, though, the work helps to illustrate how they may be mitigated through any number of regulatory or rate-making measures and highlight some of the complexities and trade-offs involved therein. So what exactly have we done? The project involves some financial modeling of two prototypical utilities, where for each utility we quantify the financial impacts of net metered PV on both utility shareholders and ratepayers. We then explore sensitivities around the size of those impacts in order to better understand the conditions under which the impacts might be larger or smaller. And then finally, we look at what happens to the size of those impacts if the utility were to implement one of various potential mitigation measures, and we'll talk more about the specific kinds of measures that we considered. And so I just want to stress that in some sense it's really those latter two pieces, the sensitivity analysis and the analysis of mitigation measures, that offer the most interesting and valuable findings from this work, as they hopefully begin to move the discussion beyond these dueling grand claims and instead try to focus on thinking about when these issues are most critical and about solutions. The last thing I'll mention here is that in quantifying the impacts of PV, we do so in terms of three specific metrics. And those are the achieved shareholder earnings, achieved return on equity, and average retail rates. And so as we go through the results, we'll be looking at the impacts principally in terms of those three metrics. So the analysis is based on a pro forma financial model that was previously developed to analyze the utility financial impacts of energy efficiency programs. And those impacts are similar to, though not exactly the same as what we see with PV. And so that model has been vetted pretty heavily through the course of these earlier energy efficiency applications that I alluded to earlier. The model requires a whole array of different input assumptions that are kind of listed in general terms in the schematic on the left-hand side here. And to develop those input assumptions, we compiled data from utility rate case filings, integrated resource plans, other sorts of regulatory documents. Based on those inputs, the model then calculates annual utility costs and revenues over a 20-year period and calculates the three metrics that I mentioned based on those cost and revenue projections. The one key aspect of the model is that, in effect, it simulates periodic rate cases every few years, where new rate cases are developed based on test year revenue requirements and billing determinants, and then the revenue collections over the succeeding years are based on those new rates. To then calculate the impacts from distributed PV, we first run the model without any PV, and so we generate those various metrics in a no PV case. We then rerun the model with PV added, and essentially what that serves to do is to reduce the growth rate of retail sales and peak demand. And then from those model runs, we can characterize the impacts of PV in terms of the changes in those three metrics that I mentioned. So suffice to say, there's a lot more detail in the report about the model, but these are the basic nuts and bolts involved. So how did we organize the analysis? As I mentioned, we looked at two different prototypical utilities. One is a vertically integrated utility located in the Southwest, and the other is a wires-only utility and default service provider in the Northeast. The analysis consists of three core elements. The first is a base case, where we estimate the impacts of PV under an initial set of assumptions for those two utilities. We then model a series of sensitivity cases where we vary some of the key assumptions for those utilities. And those sensitivity cases, as I mentioned, really help to illustrate just how sensitive some of these impacts can be to the underlying conditions of the utility. And then finally, we model a bunch of mitigation cases where we layer in different kinds of regulatory or rate-making mechanisms that utilities or regulators might adopt in order to lessen any negative impacts that may occur. One other important aspect of the analysis to be aware of is the level of PV penetration considered. So within the base case analysis, we consider PV penetration levels that ramp up over 10 years to levels that range from 2.5% to 10% of total retail electricity sales. And those numbers are quite high relative to what most utilities in the U.S. are at. At the national level, distributed PV currently represents about 0.2% of total U.S. electricity generation, and then those states and utilities with relatively high penetration levels are currently in the kind of 1 to 3% range. So that just kind of gives you some sense for how the penetration levels that we considered compare to at least the current state of affairs. The last dimensional piece that I'll mention here is the time frame. As I said, the models run over a 20-year period, but we ramp up the PV over just the first 10 years and then hold it steady at that level for the remainder of the analysis period. And we do it that way in order to capture any end effects from PV, namely any generation deferrals that may occur in years after the PV is added. We take some pains within the report, and I'll do so here to be very clear and explicit about some of the key limits and boundaries to the analysis. And we do this chiefly to preempt any potential misinterpretations or misuse of the work. And so the first thing that I'll stress here is that the analysis, as I've described, relies on this financial model. It's not a detailed operational or planning model of the utility system. And so when we estimate the value of PV, that is the changes to utility costs resulting from PV, we rely on a coarser set of assumptions than what you might find in those other kinds of models, with the trade-off being that we have a much finer level of detail on the rate making and financial dynamics. The second item to note here is that the utility costs and revenues are modeled at the aggregate utility level rather than at the individual customer level or customer class level. And so we have a fairly limited ability within this particular study to talk about cross-subsidization among customer classes. And so as a result, we really try to highlight and emphasize the shareholder impacts. And then in some future follow-up work, we anticipate looking in more depth at the impacts both within and across different customer groups and customer classes. Third, this is not a full cost-benefit analysis of PV in the sense that we're not looking at all of the broader costs or benefits that may fall outside the boundary of the individual utility. Nor is it really even a cost-benefit analysis of net metering, since the impacts that we're estimating and quantifying are based on a comparison to sort of a world where there's zero PV deployment. And of course, in reality, even without net metering, some deployment of PV would likely occur. So that's I think, an important clarification. Fourth, we're focused here on just looking at the impacts of customer-sided PV in isolation from any other distributed energy resources out there, other kinds of changes in utilities environments that may be having similar kinds of impacts on utility shareholders. And so, of course, in reality, these things are happening in tandem and their impacts interact and potentially compound one another. But for the purpose of this analysis, we're really just kind of looking at PV in isolation. And then fifth and finally, although we've structured the analysis around two very different utilities and have incorporated this fairly wide range of sensitivity cases and different mitigation cases, we certainly haven't covered every potential scenario worth considering. And so it's partly for this reason that we try to cast this work as more of a scoping study than as any kind of grand treatise. So we'll turn now to the results of the work, starting with the base case, and I'll just reiterate again that the base case analysis is intended as a vehicle for explaining some of the underlying dynamics that drive the financial impacts from PV, and also as a jumping off point for the sensitivity and mitigation cases. And so in general, I would just caution against placing any special emphasis on the numerical results here, as I think the following sections will really show how sensitive those results are to the particular assumptions and aspects of the utility environment that we impute. So with that, I will hand the mic over to Andy to take us through the results.
Thanks, Galen. So to begin laying that foundation to talk about the impacts of customer-sided PV, we'll start by talking about utility cost reductions from PV. So the impact of customer-sided PV on utility costs is a function of how PV changes retail sales and peak demand, as well as a variety of other assumptions about growth-related costs. And the manner in which those cost impacts are modeled differs somewhat between the two prototypical utilities. So our financial model calculates the utility revenue requirement as the sum of 6 cost categories, specifically fuel and purchase power, operations and maintenance, depreciation, interest on debt, return on rate base, and taxes. The largest cost category reduced by PV is fuel and purchase power costs, including some other annual pass-through costs. So for the Southwest utility, we see that PV reduces fuel costs for utility-owned generation, purchased energy and capacity costs, and RPS procurement costs. Now, the Northeast utility is assumed to not own generation and transmission, so we see that PV reduces power purchases, transmission access charges, and RPS compliance costs. And because these costs are all modeled as annual pass-throughs, PV reduces these costs on an equivalent basis with a reduction in annual sales. In our model, PV also reduces costs associated with deferred or avoided capital investments. For the Southwest utility, this includes reductions in depreciation and interest costs, return on rate base, and taxes from deferred generation, transmission, and distribution capital expenditures, and the O&M costs associated with the deferred generation. The Northeast utility sees reductions in depreciation costs, interest costs, return on rate base, and taxes from only deferred distribution system capital expenditures. We assume that PV can only defer a portion of the growth-related transmission and distribution capital expenditures, And we use a somewhat simplified dispatch logic to determine the deferral of generation capital expenditures. We'll present some alternative assumptions about PV's ability to avoid these utility costs later in the sensitivity results. But for now, we present the results from the study that show that in the Southwest utility, customer-sided PV reduces the total utility costs over the 20-year analysis period by about 1.3% at 2.5% PV penetration, and by about 4% at 10% PV penetration. This is all compared to a case without any customer-sided PV. And similarly, for the Northeast utility, the cost reductions range from about 1.5% of total utility costs at 2.5% PV penetration to about 4.5% of utility costs at 10% PV penetration. And I think an interesting result is that the cost reductions do not scale proportionally with the increase in PV penetration. So, for example, if you double the PV penetration, you don't necessarily double the cost reduction. As shown in the figures, the composition of the cost reductions differs significantly between the two utilities, and this is due to differences in their physical and operating characteristics. This has important implications for the shareholder and ratepayer impacts, and we'll discuss these later. We also see that customer-sided PV reduces both utility revenues and costs, as I discussed earlier, though the reductions in revenues are greater than the reductions in costs, especially at higher PV penetrations. In the case of the Southwest utility, the impacts on revenue and costs are roughly equivalent at the 2.5% PV penetration scenario. At higher penetration levels, however, these revenue reductions exceed the cost reductions, in part because of a declining marginal value of PV. This is one of the points that I discussed in the previous slide. In the case of the Northeast utility, revenue reductions exceed cost reductions across all of the PV penetration levels considered, and the divergence is considerably wider than that for the Southwest utility. This occurs because the Northeast utility has higher assumed growth in certain fixed non-fuel costs that customer-sided PV is assumed to not reduce. So now we get into our results on our shareholder and ratepayer impacts. So under our base case assumptions, customer-sided PV leads to a reduction in the prototypical utility's achieved ROE. So this occurs because, as discussed previously, PV reduces non-fuel revenues by a greater amount than non-fuel costs. This in turn reduces the utility's earnings and thereby reduces its return on equity. We call this reduction in ROE in the report the revenue erosion effect. Impacts on achieved ROE vary by utility and PV penetration level. So at 2.5% PV penetration, average achieved ROE was reduced by about 0.3% for the Southwest utility and by 5% for the Northeast utility. And under the more aggressive 10% PV penetration scenario, average ROE fell by about 3% for the Southwest utility and by about 18% for the Northeast utility. These ROE reductions occur because of the proportionally larger effect of customer-sided PV on utility revenues than on utility costs under our base case assumptions. ROE impacts were larger for the wires-only Northeast utility because of both its higher assumed growth and fixed costs and its proportionally smaller rate base, as it does not own generation and transmission assets. The impact of PV on shareholder earnings for the Southwest utility was somewhat more pronounced than we saw in the ROE impacts. So customer-sided PV may reduce shareholder earnings through two separate mechanisms. First, it can reduce shareholder earnings if it reduces utility revenues by a greater amount than it does costs. This is that revenue erosion effect that I talked about that drives the impacts on ROE. Second, and separately, customer-sided PV may also diminish future earnings opportunities by reducing or deferring capital investments that would otherwise contribute to the utility's rate base. We term this in the report the lost earnings opportunity effect. Under the 2.5% PV penetration scenario, average earnings for the Southwest utility were reduced by about 4%. Because of the lumpy nature of capital investments and the way in which they change the timing of general rate cases and setting of new rates, those earning impacts do not necessarily scale with the penetration of customer-sided PV. And we see under the 10% PV penetration scenario, earnings for the Southwest utility were reduced by 8%. Because the Northeast utility does not own generation or transmission, the lost earnings opportunities from customer-sided PV are less severe, and thus impacts on earnings are similar to impacts on ROE, ranging from a 4% reduction under the low end of our PV penetration scenarios to a 15% reduction in earnings at the high end of the PV penetration scenario. Within the time frame of our analysis, customer-sided PV increases average all-in retail rates. So these rate impacts reflect the net impact of customer-sided PV on utility costs and sales, where reduced costs are essentially spread over a smaller sales base. The ratepayer impacts of customer-sided PV were relatively modest compared to what we just discussed as the impacts on shareholders. So in the 2.5% PV penetration scenario, customer-sided PV led to about a 0.1% increase in average rates for the Southwest utility and a 0.2% increase for the Northeast utility. And under the more aggressive 10% PV penetration scenario, average rates rose by 2.5% for the Southwest utility and 2.7% for the Northeast utility. It's important to note, though, that these impacts represent the increase in average rates across all customers, including those with and without PV, and so they don't necessarily measure cost shifting among participating and non-participating customers. So we'll move now to the sensitivity analysis and present some selected example results from that. One key objective, as Galen mentioned, of the scoping study was to illustrate the extent to which the potential impacts of customer-sided PV depend on underlying conditions of the utility. So to explore these interrelationships, we compared the impacts from PV under a wide array of sensitivity cases, each with varying assumptions about the utility's operating or regulatory environment. The table here shows the full range of sensitivity cases that we considered for each prototypical utility. It's important to note here that while we analyzed a lot of sensitivity cases, this list is not meant to capture all possible conditions for all utilities. So a good example of this is while there are several utilities across the U.S. with revenue decoupling, we did not include decoupling in those sensitivity cases, though we did include it in our mitigation analysis. The sensitivity cases all focus specifically on impacts from customer-sided PV at 10% PV penetration. This is the highest penetration level examined in the study, and we use this for the sensitivity cases in order to most clearly reveal the underlying relationships between the impacts of PV and the sensitivity variables. In other words, to help distinguish the signal from the noise. Where lower PV penetration levels assumed, the impacts of PV would be smaller and the ranges across sensitivity cases would be narrower. But it's important to note that the fundamental results would be qualitatively the same. So we see that the direction of impacts in the base case, that being decreases in utility profitability and increases in average retail rates, were consistent across the sensitivity cases. However, the magnitude of shareholder impacts varies considerably across the sensitivity cases, as you can see in the figure. So specifically, achieved earnings were reduced by 5 to 13% for the Southwest utility and by 6 to 41% for the Northeast utility. We also saw similar ranges in the impacts on achieved ROE. So this illustrates the point that Galen mentioned early on, that the degree to which these impacts are potentially depend on utility-specific conditions. By comparison, the ratepayer impacts were relatively stable across sensitivity cases, with increases in average rates ranging from 0 to 4% for the Southwest utility and from 1 to 4% for the Northeast utility. So we'll move now into just an example of the sensitivity analysis. And here we're providing sensitivity case results that focus on the assumed value of PV. As discussed previously in the base case results, the financial impacts of customer-sided PV on shareholders and ratepayers are driven in part by the associated impacts on utility costs. So this is, the avoided cost or value of PV. Among the various sources of cost reductions we talked about, avoided generation, transmission, and distribution capacity costs are arguably the greatest source of uncertainty and disagreement. So we developed a set of alternative sensitivity cases to help better understand the sensitivity of our shareholder and ratepayer impacts from customer-sided PV on assumptions related to capacity value and avoided T&D costs. As you can see in the results, we found that the impacts to both the prototypical utilities are particularly sensitive to the capacity value and avoided T&D costs. It's important to note, and I think a really interesting takeaway from the sensitivity analysis, is that this presents divergent implications for ratepayers versus shareholders. The greater the capacity value and avoided T&D costs from PV, the greater the deferral of utility capital expenditures. What this means is that this reduces the impacts of customer-sided PV on retail rates as utility costs are further reduced. In fact, under one set of assumptions for the Southwest utility, customer-sided PV results in a slight decrease in average rates. For utility shareholders, however, the implications of this have a different effect. Increasing deferral of capital expenditures leads to a greater erosion of earnings. Many of the other sensitivity case results showed similar conclusions about how the impacts depend on particular circumstances of the utility. So for example, the impact of customer-sided PV on average retail rates also depends on underlying load growth, again, prior to the effects of PV on load. So with lower underlying load growth, as may occur, say, in the case of a utility with aggressive energy efficiency programs, customer-sided PV results in a larger increase in average retail rates because of the smaller base of retail sales over which fixed costs must be recovered, and because of the reduced opportunity for cost savings from deferred capital expenditures. Shareholder impacts from customer-sided PV can also be sensitive to underlying load growth, though these relationships are somewhat complex and can be idiosyncratic depending on details of the particular utility. We also see that the shareholder impacts of customer-sided PV tend to be more severe when retail rates rely predominantly on volumetric energy charges, and also tend to be more severe when longer lags exist within the rate-making process, for example, longer periods between rate cases or the use of historic test years. The heightened shareholder impacts in these cases occur because of greater revenue erosion associated with PV. And finally, the shareholder and ratepayer impacts from customer-sided PV also depend, though on a lesser extent, on the magnitude and growth rates of various utility cost elements. The degree and direction of those sensitivities depends on the type of cost and how it's recovered. So for example, the erosion of shareholder profitability from customer-sided PV is unaffected by fuel costs because we assume they're a pass-through, but these impacts to shareholder profitability may be highly sensitive to the capacity costs for utility-owned generation. And the full set of sensitivity cases and results can be found in the report. So we'll move now to the last element of the study, and that's the mitigation analysis. So we analyzed a number of options for mitigating the possible impacts of customer-sided PV on utility shareholders and ratepayers. These mitigation scenarios borrow from the kinds of measures that have been implemented or suggested in connection with energy efficiency programs. Most target shareholder impacts associated with either revenue erosion or lost earnings opportunities, and in some cases, those may exacerbate the ratepayer impacts from customer-sided PV. We also considered a mitigation measure to actually target those ratepayer impacts. Again, this list of mitigation measures is not meant to consider all possible mitigation approaches. And as in the sensitivity analysis, we focused on the impacts under the 10% PV penetration scenario in order to most clearly reveal the effects of the mitigation measures that we considered. We examined each of the mitigation options in isolation, but I think we should note that several of these could be coupled with each other or with other mitigation measures as part of a more comprehensive solution. So for example, combining RPC decoupling with shareholder incentives. Potential solutions to mitigate the impacts of PV may be more viable if they address concerns of both ratepayers and shareholders. The full scope of the mitigation analysis is shown in the table, and I'll provide some selected results in the following slides that are highlighted in these red boxes. The full set of mitigation analysis results and discussions of important considerations and trade-offs can also be found in the report. So decoupling and lost revenue adjustment mechanisms may moderate revenue erosion from customer-sided PV and thereby mitigate its impact on shareholder ROE. However, the size of the impacts varies greatly depending on the design of these mechanisms and the characteristics of the utility. So several regulatory tools have been used in the context of energy efficiency to mitigate the disincentive for utilities to pursue energy efficiency programs that reduce their sales. This includes various forms of revenue decoupling as well as lost revenue adjustment mechanisms. So we developed a few mitigation cases to explore their potential applicability for customer-sided PV. So revenue decoupling is designed to address the misalignment of incentives towards energy efficiency and other demand-side resources by essentially decoupling the utility's revenues from its sales. Revenue per customer decoupling is one form of revenue decoupling that allows revenues to grow based on growth in the number of customers between rate cases rather than on the growth in retail sales. Another design element of decoupling that we considered is the application of a revenue growth factor. This is commonly called a K factor. So the K factor allows the revenue, or in our case the revenue per customer, to grow between rate cases to better match growth in fixed costs. This is particularly important for a utility facing the effects of high cost inflation and high fixed cost growth. An LRAM, like decoupling, is also intended to address the throughput incentive, though it does so by reimbursing the utility specifically for lost revenues directly attributable to energy efficiency programs. Unlike revenue decoupling, which fully severs that tie between sales and revenues, an LRAM is more narrowly focused on sales reductions associated with energy efficiency programs, or in our analysis, customer-sided PV. We see in the results that implementing RPC decoupling without a K factor actually leads to a 1.2% decrease in achieved ROE for the Northeast utility, actually exacerbating the ROE erosion. And this is a somewhat counterintuitive result. This decrease in ROE is due to the fact that growth in the number of customers is substantially lower than growth in non-fuel revenues in the base case with 10% PV. So what this means is that the utility, under RPC decoupling without a K factor, collects substantially less revenues when they're tied more closely to customer growth, as occurs with RPC decoupling. And we see the same phenomenon when we implement high fixed customer charges. When we add a K factor, so RPC decoupling with a K factor, actually restores ROE back to the level achieved without PV under our base case conditions. In the case of the Northeast utility, this is achieved through a positive K factor. We also see that the LRAM improves the Northeast utility's ROE, though by not enough to achieve ROE comparability. And this is to be expected given the way an LRAM is designed and the way the Northeast utility collects revenue. The Northeast utility results show an important result about mitigation approaches, that the efficacy of such measures depends on the characteristics of the utility and the mechanisms designed. To the extent that decoupling and LRAM mitigate the ROE impacts from customer-sided PV, they do so by increasing revenues, which necessarily increases average retail rates. While these measures may mitigate the impact of PV on shareholders, trade-offs clearly exist in the form of increases in average retail rates above and beyond any rate increases that occur as a result of the customer-sided PV. In order to mitigate the shareholder impacts of lost earnings opportunities resulting from energy efficiency, utilities in some jurisdictions have been allowed to finance customer EE measures and earn an authorized return on those investments. Similarly, the lost earnings opportunities resulting from customer-sided PV could be mitigated by allowing customer-sided PV to become a regulated investment opportunity for the utilities. So this might involve full utility ownership of customer-sided PV assets, as has recently been proposed by APS and Tucson Electric Power, or may consist of utility financing of customer investments, similar to Public Service Electric and Gas's solar loan program. Utility ownership or financing of customer-sided PV may raise a variety of significant policy and regulatory questions that shouldn't be ignored. So, for example, whether a regulated utility should be allowed to provide a service similar to that provided by unregulated competitive companies. And it also raises questions around the sharing of risk, as ratepayers would generally bear some portion of the risk of these investments. So for the quantitative side, putting aside those important policy questions, we assume for the purpose of this analysis that the regulated utility recovers the PV system costs through customer lease payments and capitalizes the system costs at its authorized ROE, similar to a supply-side investment. And we considered two scenarios. One is a bookend scenario in which the utilities own 100% of the customer-sided PV capacity, and another in which they own 10% of PV capacity. As in all other scenarios, we assume these PV systems are installed behind the customer meter and interconnected via a standard net metering arrangement. So the impacts on utility billing determinants under this mitigation scenario are the same as in the base case. However, we assume here that the utility receives additional revenues from customers with PV systems that are owned or financed by the utility, and that those revenues are assumed to provide the utility both a return of and on its investment. Under the scenarios in which the utility, and in particular the Southwest utility, owns all customer-sided PV, achieved earnings rise significantly and more than offsets the decline in earnings that occurs under the base case with 10% PV. Under perhaps the arguably more realistic scenario in which the Southwest utility owns 10% of customer-sided PV, the increase in achieved earnings is only 10% of what occurs when it owns 100%. So although achieved earnings increase in the 10% ownership case, those increases do not restore profitability back to the levels that occur under the base case without PV. We also see that the Northeast utility shows similar increases in earnings, and in the case of full ownership, shows substantial increases in earnings. This is because the Northeast utility otherwise has limited investment opportunities. We do not report rate impacts here because the incremental impact to rates from these scenarios would be paid by participating customers only. The prior mitigation measures all focused on addressing impacts of customer-sided PV on shareholders, and in most cases involved some corresponding increase in average rates. In contrast to that, one option for potentially mitigating the impacts on utility ratepayers is to automatically count all customer-sided PV directly towards the utility's RPS compliance obligation. Again, such an approach also has trade-offs, since it effectively entails transferring ownership of these renewable energy certificates as a condition of service under net metering. And it achieves cost savings by, in effect, reducing the amount of incremental renewable generation required to comply with the RPS. As shown in the figure, applying RECs generated by customer-sided PV toward the utility's RPS compliance obligations offsets a substantial portion of the increases in average retail rates that would otherwise occur in conjunction with the customer-sided PV. In the case of the Southwest utility, the rate impacts were reduced by roughly half relative to our base case with 10% PV. Rate impacts for the Northeast utility are almost entirely mitigated. The degree of this mitigation depends on several factors, most critically on the cost of the avoided RECs, which in turn reflects the cost of renewable energy relative to non-renewable generation. So when RECs are expensive, allowing customer-sided PV to count towards the RPS leads to a greater reduction in utility costs and thus a greater reduction in average rates. Applying customer-sided PV towards the utility's RPS obligations does not impact utility ROE and earnings in our study, as we assume that the avoided RPS compliance costs are an annual pass-through to customers. So I'm going to conclude with some key takeaways from the study and some areas for future research. So in summary, the findings from this scoping study point towards several high-level policy implications. First, even at 10% PV penetration levels, which as Galen mentioned are substantially higher than exist today, the impact of customer-sided PV on average retail rates may be relatively modest, at least from the perspective of all ratepayers in aggregate. At a minimum, the magnitude of the rate impacts estimated within our analysis suggests that, in many cases, utilities and regulators may have sufficient time to address concerns about the rate impacts of PV in a measured and deliberate manner. Second, and by comparison, the impacts of customer-sided PV on utility shareholder profitability are potentially much more pronounced, though they are highly dependent upon the specifics of the utility operating and regulatory environment, and therefore warrants utility-specific analysis. Finally, we find in our study that the shareholder and ratepayer impacts of customer-sided PV may be mitigated through various incremental changes to utility business or regulatory models, though the potential efficacy of those measures varies considerably depending upon the design and the specific utility circumstances. Importantly, these mitigation strategies entail trade-offs, either between ratepayers and shareholders or among competing policy objectives, which may ultimately necessitate resolution within the context of broader policy and rate-making processes rather than on a standalone basis. And as a scoping study, one final objective of our work was to highlight some additional questions and issues that we think are worthy of further analysis, many of which we plan to address through follow-on work to this study and further refinements to our financial model. Instead of going through and reading all of these, we'll just leave it with that. And again, further details of this and further explanation are contained within the body of the report.
Great. Well, thanks Galen and Andy for those that presentation. We'll go ahead and start to move now into the Q&A session. We actually have about 20 minutes left for this, so we should be able to cover a lot of your questions. And just as a reminder, you can still add questions at the chat window on the bottom left. We'll continue to be looking down there for additional questions that come in. So with that, I'll start with the first question to Galen, which is how do we separate the impact of net metered PV from all the other factors that might be impacting rates over the next 20 years?
That's a good question. I think one of the sort of virtues of modeling is that it allows you to isolate individual things where you've got lots of different knobs and buttons and you can just turn one thing at a time and see what that does. So in the case of this study, we developed these prototypical utilities and sort of built out all of the assumptions that would drive the rate, the trajectory of retail rates over this analysis period. And then to look at the impacts of PV, we simply sort of inject some PV into the model, which in effect means modifying the growth rates of retail electricity sales and peak demand. And based on those changes in those growth rates, we can see what happens to these financial metrics. Of course, in reality, it's really difficult to do that because you do, as the questioner asked, have all of these different things happening at the same time. And so, when looking at how any actual utilities rates are changing over time, it can be really difficult to pick out the impacts just from PV in isolation. And that's really why we, for the purpose of this analysis, took the modeling approach.
Great. Another question was related to the distribution cost impacts of PV. So the question was, how are distribution costs reduced when facilities must be designed and sized based on the potential for little or no PV output? I'm not sure if I can answer the question directly in terms of how in reality this happens. I can kind of describe how we handled this within the context of the model, and then actually, Andrew, if you feel like jumping in, you should feel free to do so. But within the model, when we add PV to the utility, that in effect, as I mentioned, manifests as a change in the utility's peak demand growth. And so within the model, certain costs are a function of peak demand, and that peak demand we sort of specify both at the bulk power level, and that impacts generation investments. And then we also are able to specify kind of peak demand at the transmission and distribution system levels. And so within the model, we specify what the capacity credit is for PV really at each of those two levels. So PV has a certain capacity credit at the bulk power level, which then results in a certain change in peak demand growth at the bulk system level. And then at the distribution system level, we in effect specify a different capacity credit, which is basically a prorated number from the bulk power capacity credit. And that then drives any potential deferral of distribution system costs. This is, though, of course, an area of tremendous uncertainty and disagreement in terms of how PV actually impacts distribution system costs, whether it defers any costs there or maybe potentially could increase certain costs once penetration levels reach some critical threshold. And so in recognition of that uncertainty, we explored these pretty wide sensitivity cases that look at fairly widely varying assumptions about how PV impacts those costs. And those were the value of PV sensitivity cases that Andy presented. Yeah, and I just want to add that there was a question just about how do we treat the potential substitutability between utility generation and distributed PV for meeting peak demand. And that's really where it comes down to that capacity credit assumption that we have for PV And that's something that we pulled from looking at results in the literature where people have estimated the capacity credit of PV and sort of its contribution to meeting peak demand. And then also included in that is sort of a schedule at how that might be reduced as you add more and more PV, that as you add more PV, you might be shifting the time of peak net demand into the early evening, which might reduce the effectiveness of PV in helping to meet your peak needs. So we account for that through those assumptions that are input into the model. And again, as Galen said, that's a big part of the sensitivity analysis that we include to sort of see how sensitive the results are to those sort of factors. So another question along the lines of the model, this one I'll send to Andy, was have predictions of the model been compared with actual outcomes? And if so, how accurately did the model predict those outcomes?
Mm-hmm. So we have not taken the results from prior work on energy efficiency and compared them to actual outcomes. And this is simply because the way in which we represent the utilities, often on a prototypical or in some of our applications of the model, have used sort of an amalgamation of utilities to create a sort of statewide utility construct, just aren't amenable to these ex post or after the fact comparisons. And I think the other point too is that the idea here is to really generally represent the impacts in some of our earlier work of energy efficiency, and in this case customer-sided PV, as Galen mentioned, through modeling techniques of changing sort of only one variable at a time. You know, utilities in reality face various issues that they have to manage in real time, and the outcomes of that are driven by several different forces that are just beyond the modeling that we can do.
Great. Okay. And so another question for Galen. Some of the questions revolve around, does the model differentiate between different types of customers? And I think this is beyond just talking about different customer classes, but also different customers that might be adding PV. So you might have some customers that are adding PV that have higher than average bills, or you might be having customers that are in suburban versus urban areas. And the question is just, to what degree do we represent those different factors?
Yeah, I mean, I think the answer there really is not at all. I mean, within at least the version of the model that we used for this analysis, there was no distinction among different customers. So everything is happening and is being represented at the aggregate utility level, and that includes the characteristics of the PV systems that you're adding and the characteristics of the customers with PV. So unfortunately, it's all rather aggregated. In future work, we actually have made some modifications to the model that allow for certain level of distinction among different customer groups and customer classes. And so I'm hopeful that we'll be able to kind of dig into some of those more customer-specific issues in future versions of this work.
Okay. And then Andy, we've got a couple of questions that are asking about comparisons to munis and co-ops. And so let me key up a different question first, and then maybe you can also sort of touch on that question. So the other question is more fundamental to understanding what's going on in the model. And the question was, is if regulators usually set rates based on some sort of cost plus formula, then how is it that actually PV does affect profits? It seems like there would only be an impact on rates, but it wouldn't actually affect the profits of the utility. So could you explain a little bit more about that?
Mm-hmm. Yeah, sure. I think it's good to explain that first, and then try and link it to how this might have implications for municipal and cooperative utilities as well. So regulators set rates in the rate case process using some sort of a test year. Often it's a historic test year, so a previous looking period of costs, or current, in some, though very few cases, future test years. Regulators take the test year, and then based on the billing determinants, so the sales, demand, and customers, during that same period, they set and authorize a rate. So unlike a market where the price is essentially changing in response to supply and demand, regulated utilities have a price of electricity that's based on that regulated rate setting process. If expectations about the costs and also expectations about the load, if those differ between rate cases, what often happens, and is in the case of what we're looking at, when things like sales decline between rate cases, the utility is collecting less revenues than was assumed during the rate setting process. And so because they can't immediately change their electricity rate, they're sort of using the rate that's been approved in a rate case. It's that period between rate cases when utilities' sales are declining and thus their revenues that are largely collected on a volumetric basis are declining greater than any reductions in costs. That's what we see in this revenue erosion effect. Now, the lost earnings opportunities effect is mostly related to future planned capital investments that are avoided or deferred, but it's really this impact on ROE that we see from the revenue erosion effect. It's an artifact largely of the rate setting process and different outcomes than what's expected in that rate setting process. The linkage, I think, to municipals and cooperatives is that this work shows the impacts on a utility whose rates are set, again, through this rate setting process or somewhat infrequently, and whose revenues are collected largely based on volumetric sales. So it is possible in the case of municipals and cooperatives, though they don't have, they aren't investor-owned in the same sense as what we're talking about here, many of those utilities do largely collect their revenues on a volumetric basis. And so anything that could challenge that revenue collection, like customer-sided PV in isolation in this case, or energy efficiency, certainly would have impacts on those utilities.
Great. And maybe one follow-up on that is just, can you say something more about the degree to which the model includes detailed representation of each individual utility's rate structure?
So that's a good question. In the model that we used for this analysis, we were able to use a somewhat simplified allocation of the utility's costs among a customer charge, demand charge, and energy charge. We held those allocations consistent throughout the analysis period. And again, those allocations are done at a utility level because we didn't do, as Galen mentioned, this sort of specific customer class analysis. And so we were able to allow those allocations to set a customer demand and energy rate. It turns out that both of these prototypical utilities in our base case largely collect their revenues from an energy rate, so largely based on volumetric sales. We varied these assumptions in the sensitivity analysis, and then we also looked at approaches related to, say, a high fixed customer charge, so change the allocation to get a high fixed customer charge in the mitigation analysis, and we also looked at a higher demand charge in the mitigation cases. So we do have the ability to vary that, though it's somewhat limited by the fact that things are on a utility basis. We are and have changed the model to be able to do more detailed underlying rate design related to inclining block rates, time of use rates, more detailed customer class level assumptions about those allocations.
Okay. Galen, this is a potentially challenging one, but I'm interested to hear your thoughts on it, and I can weigh in too. But the question was, would a value of solar tariff protect a utility from some of the insufficient revenue collection issues that we're seeing here? And would this both protect against the revenue erosion effect that we see and also the lost earnings opportunity effect?
I think in the end it ultimately just comes down to what the price of that value of solar tariff is relative to, in a sort of the average price at which customers are compensated for PV production under net metering. So it's, I think, although it would be modeled differently in terms of the revenue and cost flows, I think that in the end it ultimately just comes down to what the number is.
Yeah, and then in terms of that last question about would it affect both the lost the sort of revenue erosion and the lost earnings opportunity, the lost earnings opportunity really comes from the fact that PV can displace capital investments that the utility would otherwise be making, such as in generation expenditure in the Southwest or in distribution expenditure. And so if you had a different mechanism of compensating customers who add PV, you'd still have the issue that PV would displace some fraction of the utility's investment opportunities, and so there would still be this sort of lost opportunity effect. But going back to Galen's point, the revenue erosion effect kind of deals a little bit more with how does that compensation line up with the avoided costs of PV. Okay, and then Andy, maybe we could kind of go back into the mitigation analysis. There was a couple of questions, just if you could clarify a little bit more about exactly what is a K factor, and then could you also say a little bit more about what the LRAM stands for and where that comes from?
Mm-hmm. Sure. So the K factor is common term to really represent any sort of a design element that allows additional growth in revenues between rate cases using a decoupling mechanism. So what you're trying to do there is, in the case of a utility that's facing high cost inflation, high fixed cost environment, to things like, say, labor costs or pension costs that are difficult for them to control. You know, they're sort of a fixed growth, and they really can't reduce those between rate cases. For utilities facing those environments, the decoupling mechanism alone will not necessarily match the growth of those costs between rate cases. So you use a K factor, it's really a percent, either positive or negative, to allow those revenues to grow between rate cases and better match those high fixed costs. An LRAM is a lost revenue adjustment mechanism that, you know, again, is its essence is like decoupling and intended to address the throughput incentive, but it's only functioning by taking the sales that were directly attributable to energy efficiency, or in our case, PV, and reimbursing the utility revenue, those lost revenues. Okay, so I think it's actually an interesting thing we discussed with the LRAM is that in practice, implementation of an LRAM can be contentious because it requires an estimation of the amount of energy saved as a result of the energy efficiency programs. But in the fact of customer-sided PV, an LRAM may actually be easier to implement for PV than for energy efficiency, because PV production can be directly metered, whereas, you know, changes in sales due to energy efficiency is a bit more speculative or a bit more art than science. So that's a sort of an interesting thought about LRAM's application for the PV.
Great. One other question is coming up around just what the impact is of load growth, and sort of both how do we account for sort of potential for flat load growth in some of the different regions that we've studied, and then also what might be changing if we have a rollout of electric vehicles or more electrification of energy sources.
I'll take a stab at this. So we, for both our prototypical utilities, we looked at forecasted load growth in the regions in the Southwest and the Northeast to establish our base case assumptions. For both utilities, we saw we had some growth over the 20-year analysis period assumed in the base case for both energy, for retail sales and for demand, as well as some customer growth. We, obviously test this assumption in our low load growth sensitivity case, which showed that it certainly had implications on the impacts. Your point about the electric vehicles is interesting. Presumably on a sort of aggregate basis, a large amount of electric vehicles would certainly increase the utility's load. All else being equal, it would potentially reduce some of these impacts that we've seen, because the utility, if it were still collecting revenues largely based on its volumetric sales, would be selling more electricity and thus collecting more revenues. At the same time, there's a lot of important implications on the system for a large influx of electric vehicles, a lot of issues that are outside the scope of this study.
Okay. And with that, we're now approaching the top of the hour, so we're going to have to wrap up the Q&A session. We will try to address some of these remaining questions that came in via email or some other mechanism like that. And we'll also be posting a recording of this webinar at our website. That's the emp.lbl.gov. And we really appreciate you all attending this webinar and bringing these great questions. And we'll look forward to speaking with you again. And thanks for that.